Hello, lovely people. We are here once again on the course Applied Electricity. And today, what I'm taking you guys to is Thevenin's theorem. Now, I believe you guys, one way or the other, you've done something about Kirchhoff's law. That's Kirchhoff's first law that deals with finding currents um, within a junction or at a junction. The current coming in is the same as the current going out, and also to how to deal with loops, that is combining the current and the resistance to their respective EMFs or the voltages. So I believe Kirchhoff's first and second law, you are well acquainted with it. Now, what is the difference that Thevenin theorem will give us? Now, Thevenin gave a theorem, and this is how the Thevenin theorem goes.
So any linear circuit connected between two terminals can be replaced by a Thevenin's voltage in series with a Thevenin's resistance. So in Thevenin, we need a Thevenin's voltage and a Thevenin's resistance.
Okay, so now with Thevenin's theorem, we realize that there are two main things we are seeing in Thevenin's theorem. One, the first thing we are seeing is the Thevenin's voltage. And the second thing we are seeing is Thevenin's resistance. And we know that the Thevenin's voltage is represented by VTH, and the Thevenin's resistance is represented this way. So these are the two things we are seeing in Thevenin's law.
Okay, so step 1, remove the resistor from the circuit and mark the two terminals as shown in the diagram. And step 2, find the opposite circuit voltage, which is VTH, across the terminals by applying the Kirchhoff's voltage law. Step 3, record the circuit created in step 1 and deactivate all sources. Use short circuit voltage sources and open circuit current sources. And then step 4, find the total resistance of the circuit resulting from step 3 as seen from the two terminals. Step 5, reproduce the Thevenin's equivalent circuit and connect the resistor whose current is to be found. And step 6, you calculate the current in the circuit in step 5, and this current is being sought.
Or theorem. So now, when we come to this question, to analyze critically this question very well, I took you guys through the slides, that is the steps for Thevenin's theorem, or how you can go about Thevenin's theorem. These are the two main things. But with this particular question, how do you go about it? I'm going to solve this question, and I'll try as much as possible to also solve another question before this video goes to an end. So now, the whole idea about Thevenin is that, you see, when you're dealing with Kirchhoff, you have to apply a whole number of loops and simultaneously calculate the current within each loop, or the current that passes through each resistor in the loop or in the electric circuit diagram. But Thevenin, you can go straight forward to the particular resistor and calculate the current within that resistor. So that is what Thevenin is giving us. So now what happens is that when you are able to calculate your Thevenin voltage, and you are able to also calculate your Thevenin resistance, now you can find the current within that particular loop, within that particular resistor, and that current will obviously be the voltage according to Ohm's law, which is IR is equal to V. So therefore, R is equal to what? V on R. So now we need the voltage, that is the Thevenin voltage, divided by the Thevenin resistor or resistance plus the resistance in that particular resistor. So now that particular resistor we want to find the current is the R here, the current that passes through. So the Thevenin resistance we find plus that particular resistor within is what we are looking for. Okay. So now back to this question. With this question, we want to find the current that will pass through this 3 ohms resistor. We want to find a current that will pass through only this 3 ohms resistor. So we don't need to go back to the Kirchhoff and finding the loops here, B, C, D, clockwise, and this kind of things. No. We are going straight forward to find the current within the 3 ohms resistor. So finding the current in the 3 ohm resistor, and Thevenin will help us. So now, considering the step 1 and step 2 of the principles I gave you, this is what you can see from this very diagram. We have to redraw the diagram. And the step makes us understand that we should put 2 points at the ends of the terminal of this very resistor. So this resistor, I want to find the resistance within, you should put 2 ends terminals there. So now we draw our first diagram. This is 42 volts. This is 12 ohms. Point B. So now when we move to, and this 6 ohms. Now, when you get to the 3 points, that's the 3 ohm resistor. Then what we can do here is that we put terminals, an open circuit terminal over there. So now AB. Now after putting this terminal over there, here is also 35 volts. Okay. Sorry. Okay, so A, B, C, D, E, and F. Okay. Now after putting this terminal there, we introduce our Thevenin voltage. So let's introduce our Thevenin voltage in this direction. Thevenin voltage in this direction. Now, after introducing our Thevenin voltage, our interest here is now to find the value for the Thevenin voltage within this open circuit. We want to find the value for the Thevenin voltage here within this open circuit. Now, to find the value for the Thevenin voltage here, what do? We can consider this loop or mesh, and we consider this loop to find the final voltage here. Because we have a voltage here, we have a voltage here, and we have another voltage here. But this is the Thevenin voltage. So to find this Thevenin voltage, we can consider this loop and consider this loop. So now, we now like to apply the Kirchhoff's voltage loop. Now, upon applying the Kirchhoff's voltage loop, let's first take our first loop. Now, with this one, we don't need to classify whether it's clockwise or anti-clockwise. How we write the points within this loop would determine whether it's clockwise or anti-clockwise. So, for example, I want to take this very loop, and I'm taking the loop C, B, here is E, C, B, E, D, and back to C. So this is a loop. Now this loop I took, no one should tell you that this loop is anti-clockwise. It's anti-clockwise because I took it from this direction. So it's an anti-clockwise direction. So now when I took this loop I took simply means that the current is flowing, the current will be produced here. But when this very current gets here, it will not be able to pass. It's what you should take note. Now, the only current that will pass through this 6 ohm resistor is the current that is being produced from this part. So let's say the current that is being produced from this part is I1, and the current that is being produced from this part is I2. The only current that is able to pass through this 6 ohm resistor is also I1, because when it gets here, it passes here. This I1, same I1 gets to this 6 ohm resistor. Why? Because this part is open circuit there. Open circuit simply means there's an infinite resistance. Infinite resistance. So it will resist every current that passes. So all the currents have to come back and pass through the 6 ohms. So this is the diagram. So upon knowing this diagram and you're taking this loop, what do we do then is that now there's a voltage here which is 35, and this voltage is moving in this direction because the current is moving in this direction. This is the positive. So now there's another voltage here which is plus the Thevenin's voltage. Now the voltage diagram, you are applying Kirchhoff's law. So the sum of all the EMFs should equal to what? The sum of all the potential differentials. That is the current times the particular resistor it is going through. So now, what in this loop, when we take this loop, we only see one resistor here. And what current is passing through that resistor? That is what? I1. So now you calculate that current, which is 6, which is equal to 6 times what? The I1. And this is our first equation because we have another voltage here. So now to take this one to, let's take it clockwise because the current will move from this part going. So taking loop A, B, E, F, and back to A. Now when you take this particular loop and want to calculate, you can also get the voltage, which is 42. It's only one voltage. It passes through 12, and the same current also passes through 6, the 6 ohm resistor. So that means if the same current is passing through, we can just equally say that it's equal to 12 plus 6 times I1. 12 plus 6 times I1. Now, from here, we can calculate, which is the equation 2, we can calculate for I1. So now I1 will simply be what? 42, which is equal to 18 what? I1. So I1 is simply what? 42 on 18 ampere, which is equal to negative. So the current we calculate here will give us 42 over 18 ampere. So you can use a calculator to break it down. Now, when you put that 42 over 18 ampere here into equation 1, you can find the Thevenin voltage. So now the Thevenin voltage becomes 35 plus the Thevenin voltage, which is equal to 6 divided by 42 on 18. Now 6, you can do your own calculation. Since those here, 3, 6, 3 is 18. So now you can do your own calculation in the house. So we get the Thevenin voltage to be simply equal to, that is 42 on 3 minus 35. So now the Thevenin voltage finally will give us minus 21 volt. So when you do a calculation, we are having the Thevenin voltage as minus 21 volt. Okay. Now the next thing we do here, or we can do to this one, is that we have to find the Thevenin resistance. We have to calculate also the Thevenin resistance. How do you go about calculating the Thevenin resistance? Okay, so now upon calculating the Thevenin resistance, we need to also short circuit all voltage sources within the electrical circuit diagram. Okay, so let me clear this. Okay, so we had, let me put the Thevenin voltage, we had minus 21 volt. So now I want to calculate for the RTH, which is the Thevenin resistance. How do you go about that? Now, the same place, you put the RTH at the same place. But before we can put the RTH, we have to short circuit all voltage sources. You have to short circuit all voltage sources. So now, we redraw this and we short circuit it. And I think we've done, you know the meaning of short circuit because we treated it in previous videos. So 6 ohms. We come here. So at this point, what we do is that you put the RTH, that's the Thevenin resistance, and we short circuit the 35 ohm, the 35 volts. Okay. So now, when you short circuit this, we are left to find the Thevenin resistance. How do you go about finding the Thevenin resistance? Now, to find the Thevenin resistance, we realize that this 12 ohms is parallel to this 6 ohms. So once we just find the resistance, the value of the resistance, that's the effective resistance. So the Thevenin resistance here will simply go to the effective resistance of the resistance left in the circuit diagram. So now the effective resistance of the resistance that is left within the circuit diagram. That's also, you realize that you have 2 ohm resistor and 6 ohm resistor. But the 2 ohm resistor and the 6 ohm resistor are parallel to each other. You've done resistors in parallel, so you can go check on it. They are parallel to each other because they will experience the same voltage across them. So they are parallel to each other, but they differ from different currents because this is not an open circuit, it's closed. So if the current was supposed to even pass through, different currents will pass through them. So when the current gets here, some will divert here, some will divert here. So it is parallel to each other. So the 12 ohm resistor is parallel to the 6 ohm resistor. If it's parallel to the 6 ohm resistor, then what is the effective resistance? So therefore, 1 over the RTH will simply be equal to 1 over 12 plus 1 over 6. Because that is the formula for finding effective resistance when the resistors are in parallel. So when you do this, the RTH you get here will be 4 ohms. So when you calculate this, you'll be getting 4 because this one will give you 12 times 6 divided by 12 plus 6. And you get 4 ohms as your RTH. Now, after getting your RTH, the last diagram you draw is to find the current actually this 3 ohm resistor. So now what happens is that you now introduce the 3 ohm resistor. So you introduce your Thevenin voltage, you introduce your Thevenin resistance, and now you introduce the resistor, which is the 3 ohms, in which you are finding the current. So now the current that will pass through this, let's call it I, is the current that will pass through this 3 ohm resistor. And now this current can simply be found. So how do you find this current? So this I simply now becomes the VTH all divided by RTH plus this 3 ohm resistor, because it is in series. Now the 3 ohm, this, because the same current will pass through them, they are in series. So when that happens, we have minus 21 volts from what we got. The output we have 4 plus 3 volts. So now when you do this, you are getting minus 21 divided by 7. And that will give you minus 3 ampere. So this is the final. So the current that will pass through the 3 ohm resistor is minus 3 ampere. And this is Thevenin's theorem.